Hello, I'm Elena Schmieder, and this is my team. With me today are Ed, Wojtek, Gonka, and Kevin, and we're going to discuss the details of our project, which is the sustainable design proposal for the Rolling Hills Park in Peters Township. So on the slide, you'll see our outline. These are going to be our topics of discussion that we get through today. And each one of us are going to take turns speaking about our areas of research and walk you through our project design and its sustainability contributions. So our project is located in Peters Township, Pennsylvania. It's a small, affluent community just outside of Pittsburgh. Following the closure of a golf resort a few years ago, the 200 acres of land the resort once inhabited on was acquired by the township, while the other half was actually obtained by the school district. Rolling Hills Park will be situated on 90.7 acres of land, which is right next to a newly built high school. And the township is now seeking development plans and has engaged an engineering firm. A plan has been drafted, but an official park design has yet to be adopted. The township hopes to improve the community's quality of life through the 3 pillars of sustainability, and parks and recreation play a critical role in habitat and ecosystem preservation, engaging the community, connecting people, attracting businesses, and increasing neighboring land values. Our design and goals align with the township's goals for the community improvement and engagement, but we achieve these goals through the emphasis of sustainable development. Our project proposal will focus on the North Valley section of the park and only a portion of the overall park design. Using the illustration provided by the engineering firm working with the township, we have mapped our project design. And our main focus is a 6,000 square foot net zero nature center. While the firm's plans include a nature center, there are currently no real published plans for a sustainable design. The nature center will feature a green roof and attached greenhouse in our proposal. Also included is a 500 kilowatt solar array, which will provide enough power for the nature center as well as park features included in the township's current working design. The nature center will also employ a geothermal heating and cooling system, and a biodigester is also proposed to heat the greenhouse, produce fertilizer, repurpose food waste, and act as an education tool. Last, we have included information about planting native meadows to enhance the park's triple bottom line. And on this slide, you can see our project objectives. Our project objectives seen here have a strong focus on the 3 pillars of sustainability. Overall, we seek to produce a project that will have lasting positive influence on the community. And with that, I'm going to hand it over to Wojtek for our stakeholder analysis.
Okay, hi everyone. Wanted to mainly talk about the key stakeholders on this slide here, and obviously Peters Township being the most important one, and in this case really some of the things Elena already mentioned. We really want Peters Township to take credit from implementing accepted environmentally friendly technologies that would help mitigate air and water pollution in the region. And through the tactics that we mentioned, the 3 primary tactics being, renewable energy, energy efficiency, and education, is really where we want Peters Township to focus on to kind of take the township to the next level. And the school district is important in our case just because it's on the neighboring piece of land. Unfortunately, the school itself was fast-tracked in terms of design and build, and there were very few sustainability features implemented. So there's a chance now to really engage the school primarily on having input on what the curriculum could be at the Nature Center for the educational side. Plus, Kevin will mention later, a virtual net metering scenario is also possible with the high school. And again, the key stakeholders, they have a high power, high interest. Just briefly, you can look at the little graphic there I provided, 1 through 3, and this isn't perfect, but showing that they have a high interest and a high power, the key stakeholders. And then we get into some of the primary stakeholders, and Primarily those will be local developers, design firms, architects, construction firms, HVAC companies in the area that want to get involved. And some of those are scattered. I won't go through the individual numbers, but like 13, 8, 9, and 14, you can see that those stakeholders are starting to have less power in this process, but still a very high interest. And last, I just wanted to mention that we did reach out to quite a few stakeholders. We actually did engage stakeholders for this project. Ed got to work with the township, with the Environmental Quality Board, which is another key stakeholder within the township. We reached out to the Green Building Alliance in Pittsburgh. We talked to an architecture firm, Fisher Architecture in Pittsburgh, Wade Heating and Cooling in the area, and then we also reached out to the Audubon Society of Western Pennsylvania to help us with planting the native meadows. And that's pretty much it. We can go to the next slide.
So the design of the structure itself, we wanted to embrace high levels of energy conservation and the adoption of renewable energy. So we stuck with a traditional passive solar design features. So our structure has a lot of south-facing glazing. The structure itself is as designed, would be cast in place concrete, which would provide a lot of thermal mass to buffer heat, outside heat and cooling swings, and allow for the temperate interior space. We also plan to have the north side of the building, northwest and northeast walls would be earth bermed, so they'd be protected again from swings in outside weather or temperature changes. And we included, as the design shows, an airlock entryway to keep the warm air or cool air inside the building as people entered and exit the structure. The building features if we go to the next slide, the building features a central tower that will provide an opportunity to produce a chimney effect to cool the building during the summertime with the natural convective currents that will rise and flow out through the central portion of the roof structure there. And we designed the building also with an ample roof overhang that will provide summer shading and lower the heat demand when it comes to cooling requirements. The glazing itself that we specified would be high emissivity glass with a 1/2 inch airspace, double pane, and argon filled, so they would be pretty stout thermal performers when it comes to efficiency. And the roof design, as was mentioned earlier, we plan to put a green roof on the flat surfaces on either side of the central tower. And we'll go to the next slide and talk about the green roof features.
Great. So our plan includes a lightweight, extensive green roof. The green roof will total approximately 7,000 square feet and consist of a series of layers, each serving a specific purpose for the roof's lifespan and efficiency. The roof design will cater to the site's features, taking into account the structure's exposure, weather conditions, leaf cover, roof slope, and available substrate. The roof's life cycle is more than twice that of a conventional black roof and requires less maintenance. And a green roof was important to this project for education and the efficiency it provides the building envelope. A green roof's thermal resistance and passive cooling effect will lower the stress on the HVAC system. And studies actually showed that structures with no to moderate insulation see better energy reduction results when fitted with a green roof. It is for this reason that only a moderate amount of insulation was necessary to the structural design. So why choose a green roof? Green roofs provide a multitude of benefits. Most center on its contributions to the environment, energy conservation, and costs. This particular roof will serve as an educational tool for the community, giving it social value as well. Residents can learn more about the functionality and benefits of a green roof with the hope that residents will consider building their own or at least using the same principles of stormwater retention and providing natural habitat. I've included a short life cycle cost analysis to compare the green roof to a conventional black roof. At a glance, the black roof appears more advantageous. However, the lifespan of the green roof actually puts that one at the advantage. The green roof's higher lifetime service and maintenance costs listed here may also decrease slightly if the biodigester that we've included in our design can produce enough fertilizer to service the green roof. And energy savings anticipated from the use of this green roof would further put the green roof at a cost advantage. So given the numerous advantages provided in this cost analysis, as well as the environmental benefits, the green roof has the edge over the black roof. The green roof also has the ability to engage the community, giving the green roof additional social value as well. So overall, a green roof is a practical investment from a community-focused, environmentally conscious, and financial perspective. Now we're going to move back to Wojtek for geothermal.
Okay, guys, so we decided to go with a geothermal system, a water-to-water heat pump, and we are going to use, we're proposing a closed system loop, or closed loop system. A couple important things to mention here, the benefits. We are proposing a zoned space. So we have established 4 zones at in this case, and that gives us the ability really to maintain the kind of comfort temperature that we want in each zone, and that's going to be really important for a building that's going to have maybe a lot less usage in the nighttime, potentially a lot more usage on the weekends. A couple things I wanted to mention before I go into the benefits, just some of the assumptions here. The nature center doesn't have to be super cold in the summer. It's going to be well constructed, and with some of the things Ed mentioned, we're going to incorporate the overhangs, the passive features to really limit the amount of radiant load we have on sunny summer days. So those are just some of the initial assumptions I wanted to mention. To continue with the benefits of the system, maintenance is a really big one here, because when you have 4 separate units that are maintaining the comfort in the building, individual units can be taken down without shutting the entire system down. Probably the biggest benefit that we saw early on in the initial design is, almost everywhere I looked, geothermal systems were promoted to show about 40 to 50% in energy reduction. And so that's really important. That really caught my eye, and that's why we decided to go with this ultimately in a detailed design. Has fairly low operating costs. The system replacement is at 25 years versus 15 for a typical air-to-air heat pump, which again is a very big win. This really prevents disruption to the nature center and allows the system to run for 10 more years without major maintenance. And we also decided to, geothermal systems can be drilled in 2 different ways. You can have a horizontal system or you can have a vertical system. We decided to do a vertical system because it minimizes the land disruption. There's a lot more land disruption associated with the horizontal drilling system. So we went with vertical. Let's move on to the heating component. We decided we are proposing a radiant floor heating system. The entire floor will act as a heat source. And with a radiant floor heating system, the air temperatures tend to actually be warmer at the floor. And if people's feet are warm, they generally tend to feel warmer than they might actually be. And so that's really important. We can maintain lower temperatures in the building, plus radiant floor heating really helps with cutting down on air infiltration, because a lot of the warmer air is staying towards the bottom. and the floor itself has the potential to save energy up to 20%. Okay, we can go on to the next slide. And I'm not going to spend too much time on the next slide. Just wanted to mention, okay, so this is our proposed layout. We are proposing the 4 units. As I mentioned, we want to have four units, 4 zones. And this just simply shows you how the radiant floors plan is set up. You have the hot water going in to help heat the floor, and then you have the cold water return back to the units to go back out again to heat the floor. So we can keep going. For the cooling portion of our of the Nature Center, we are proposing a variable air volume system with an economizer package. The benefits really to a variable air volume system is it's a decentralized system, and the main thing that it varies from other systems is it maintains a constant temperature, but it varies the air volume. And so the second point here, we can see there's quite a few advantages to this type of system. More precise temperature control, which is what we're looking for definitely. Reduced compressor wear. System fans tend to be one of the biggest energy consumers of HVAC systems. So we have lower energy consumption by the system fans, and then we allow for passive dehumidification. The system also is really positive in the sense that we're going to have enthalpy control, and the system will measure the temperature and the humidity outside, and if it's suitable for cooling the space, then we're just going to be using, the system will use just the blower, and that will help save energy. Okay, we can go on to the next slide, please.
Thanks, Wojtek. Moving on to the solar array. Anytime you want to achieve a zero carbon output, on-site renewable supply is always important. So we decided to go with a solar PV ground-mounted system with a total size of 500 kilowatts with a potential scale-up option. This will be located in the northeast side of the park along the gas line. And just please note that some trees will have to be removed in order to install the system. Next slide, please. So the estimated output or the size of the system was really based off the annual park load estimate. Ed calculated the annual park load estimate based on the peak load of each facility. The annual load estimate came out to be roughly 560,000 kilowatt hours annually. And the annual estimated solar output of the 500 kilowatt system is roughly 613,000 kilowatt hours annually. So this would be enough to cover the entire park's load, and the majority of the output would come in the spring and summer months. Next slide, please. Moving on to the financing and available tax credits available. The township can enter into a tax equity financing option. This is where a third party can pay for the upfront capital costs, so the township wouldn't have to pay this steep upfront capital cost for the system. And this also allows the township to enter a purchase power agreement, or a PPA. And a PPA can allow the township to receive a discounted energy price. We estimated around 25% savings. And then the township can have the option to purchase the system after year 5. There's also a federal solar investment tax credit available, or ITC. Now, if the solar array is constructed by 2019, this will be a 30% tax credit. However, there is a gradual step down until 2022, where the tax credit reduces to 10% from 2022 onwards. So you can see the chart on the right, the additional cost if construction is delayed. So the capital cost will rise as the investment tax credit decreases. So the construction date is pretty important. Moving on to the next slide, as Wojtek mentioned earlier, the virtual net metering option. This is made available from the Pennsylvania State Utility Commission, or PUC. there'll be multiple facilities within the park, each having a meter. So this virtual net metering allows all those meters to be combined under one account. And the virtual net metering process essentially banks any excess power generated from the solar PV system. So when the supply of the system is greater than the park demand, the township can bank those kilowatts. And then the township can use those banked kilowatts when the demand of the park is greater than what the system is outputting. So that's really useful when the summer demand peaks in the hot summer days. However, I will say that the 500 kilowatt system limits the capability of the virtual net metering as the park demand is close to the output. So it leads me into the next slide of our scale-up option. This option would increase the size roughly 4 times to 2,300 kilowatts. This increases the output to about 2.8 million kilowatt hours annually. All of the financing and tax credits will remain the same. However, the construction start date is a little bit more draconian as you're dealing with higher capital costs, so that decrease in tax credits is a little bit more steeper additional cost, as you can see in the chart to the right. If the construction doesn't get started until 2022, you're seeing $800,000 additional cost there. However, the virtual net metering comes more attractive as the township will be able to bank a lot more kilowatts and be able to the high school to be able to use that the excess banked kilowatts throughout the year. So the virtual net metering is a lot more attractive under the scale-up option. Moving on to the next slide. I wanted to point out, we also looked at a solar carport for an alternative design method. Same 500 kilowatt system. This we located in the adjacent parking lot next to the nature center. Some of the additional benefits that a carport structure has rather than a ground mounted system is it creates a vehicle shading for community members and potential for a car charging station. However, getting into granular details about it, it was roughly double the cost of a ground mounted system. And simply the double the cost, it really just outweighed the benefits of the shading portion. So we decided the ground mounted system was more viable. And now moving on to the biodigester and greenhouse.
Thanks, Kevin. I will be talking about energy option we used in this project. Food waste is an important problem in the world. Estimates are as high as 50% and poses a great danger for food security and GHG emissions in the future. We want to include a bioenergy technology option in our project to show how energy can be produced by using our food waste and educate park visitors. We picked a small biodigester to generate electricity and heat. When we look at the feedstock potential around the park, the most feasible one seems to be Peters Township High School across the park. It has 1,400 students. Its cafeteria itself can produce 140 pounds of food waste every day. But summer break will cut the feedstock source. At this point, food waste collection bins in the park can provide enough feedstock because parks are more active in summer. There will be picnic areas, pavilions, and food stalls in the park. All can add up to needed food waste amounts. Next slide, please. After finding out available feedstock capacity, we decided to use a small biodigester and picked basic horse 8025 model from Impact Bioenergy. It comes in a standard shipping container with built-in electric generator, gas storage tank, and other control mechanism. It is a compact and modular system. It needs 135 pounds of food waste daily. This model doesn't have high energy outputs, 15,000 BTU per hour or around 3,000 kilowatt hour electricity annually. We envisioned the horse as an educational system, so low energy output is not a concern. Also, it can divert 20 metric tons of CO2 equivalent GHG emissions from landfills each year. Next slide, please. We decided on a small heating application that would be in harmony with the nature center and agreed on a greenhouse. We placed the greenhouse in front of the nature center where it faced the south. It would get plenty of sunlight. Based on horses' output, we found out that a 200 square foot greenhouse would be perfect for our project. We also assumed that a rainwater collection tank could be used with a passive irrigation system to minimize water demands. It will be a complementary system to the biodigester in multiple ways. The greenhouse will use bulk biogas and fertilizer outputs and serve as another educational system for visitors and especially students. Next slide, please. Here on this slide, we have an operation strategy for both systems. The horse will produce fertilizer year-round. Any excess fertilizer from the greenhouse could be used in the park, high school, or could be sold. Based on outside temperatures, we assume that the greenhouse will burn biogas for 7 months from October to April, and electricity will be generated for the remaining 5 months. This electricity could be fed to the nature center. With that, I will hand over presentation to Alina. She will talk about native meadows.
Thank you, Gonka. So we're actually looking to employ perennial native meadows. The native meadows are fields or small yards that are exclusively made up of Western Pennsylvania native plants. These fields can increase the aesthetic appeal around the park, and they actually make excellent transitions to wooded areas, but can really be planted anywhere in the park. Native vegetation offers a stable habitat for native wildlife, providing local species and specifically pollinators a place to thrive. The meadows can be planted by the community, which will also build a stronger connection between residents and the park and nature. And the many benefits they offer touch on each of the 3 pillars of sustainability. So the land can be rehabilitated following the park's construction and prolonged use as a golf course, which likely used heavy amounts of pesticides and non-native grass. The lawns are low maintenance, requiring mowing just once a year in its maintenance phase. And native plants are well acclimated to the area. So fertilizers, pesticides, herbicides, and water are all unnecessary, which saves the park from having a sprinkler system or a watering schedule for the native gardens. And if they plant just a 10,000 square foot meadow, it would actually conserve between 2.6 and 8.8 million gallons of water over 20 years. So compared to other lawn types, that's pretty significant. So native meadows are self-sustaining, especially perennial meadows with no need for annual replants. Environmental risks such as carcinogens, radiation, ecotoxicity, minerals, and fossil fuel use are pretty minimal. Local ecosystems and biodiversity are strengthened with the provided natural habitat, and stormwater runoff is minimized. The deep roots of perennials actually play a really large role in water absorption. And costs are minimal, especially if the community is involved in the planting process. So now we're going to get into the economic analyses.
Okay, everyone, I'm back. So next we'll talk about the economic analysis that went into the HVAC system. And The first thing we'll start with is, one of the things I learned, and I think we all learned, is scoping an HVAC system for a new building is definitely not an easy task. It's definitely easier, I think, for existing buildings, but in this case, we had to start off with the two most important things, and that's calculating the heat loss and the heat gain of the building. Ed really kind of Ed started with the architectural drawing, so that gave us a really good starting point. The length and the width of the building are mentioned in point number 2, 144 feet in length, 48 feet in width, and that gives us roughly a square footage of 6,912 square feet. And so that's the assumption that we went for the total square footage of the building. So, the heat loss calculation, as you can see in the graphic on this slide, requires 3 main inputs. It requires the square feet of the wall area, of the individual wall areas, the glass walls, doors, and the ceilings. We have a corresponding U value for each of the wall areas, and then we assumed delta T, which is the most extreme change in temperature that we can expect, and that would be in the cooling or in the heating months. We assumed 65, so we want to maintain 65 degrees in the building, and we're assuming the low temperature will be 0. And then, as you can see, we went on in the graphic, we went on to calculate the total wall heat loss to be 62,620 BTUH. And so now we have to go, next slide please. Part of the heat loss calculation is also figuring out air infiltration. And as you can see on this slide, we used a standard formula. Ed actually provided a lot of this information to us. As you can see, the values are included to see what the total room volume will be. Again, delta T is assumed to be 65. The air changes per hour are estimated at 0.5, and then there's a constant. So for the total, for the air infiltration, 95,940, and then we went on to add both the wall heat loss plus the air infiltration to come up with a number of about 160,000 BTUH, which is what we estimated our heat loss to be. Now we will go on a little further in the economic analysis. I did want to point out here some of the assumptions that we made are listed in point number 4. And the one thing I wanted to note too is when I get to the next 2 slides, I want to make you aware we did 2 scenarios for this analysis. And the only difference between the 2 scenarios is the price of electricity. So in one scenario, scenario 1, we assumed 10 cents per kilowatt hour, and in scenario 2, we assumed 7 cents. And so that will slightly change some of the life cycle numbers. Just wanted to make you aware of that. So next slide, please. Okay, and on this slide, we are getting into how we calculated the life cycle costs for this project. The main thing, another important thing to note here that's not listed is we used the BEST tool. It's a building efficiency system tool that was provided by the Hydronics Industry Alliance. And so I think this industry is really into the geothermal area, and they provided this pretty cool tool for us to use. The tool is not perfect. Dan looked at it and said for the purpose of the project it's good. And primarily what I was looking for to gather from this tool was how much electricity are we going to consume for our system. And then in order to properly calculate the life cycle cost savings of the proposed system, you have to compare it to another HVAC system. And so for the purpose of this analysis, we chose system 2, the comparison system, as a standard electric air-to-air heat pump, which is a common installation. As you can see in point number 2, our initial assumptions came true. The annual electricity of the proposed geothermal system is less than half of the air-to-air heat pump. So right away, we are saving a lot on energy. The formula that we used for this project was slightly simplified for the life cycle cost savings. There's really 3 main things here. We're looking at the initial capital cost, which you can see clearly from the graphic there on the bottom right that the geothermal system costs almost twice as much. So that's the first thing. We look at the net present value of the energy costs, and that is listed there too. 41,658 for system 1 and almost 88 for system 2. Then we can also take a look at the net present value of the maintenance costs. And then we also consider replacement cost. And that's another thing I mentioned earlier on in the presentation. You can see system 2 needs replacing at year 15 at a cost of almost $52,000. So when you take everything into consideration, all these costs that I mentioned here, in scenario 1 with the price of electricity at 10 cents, this system is life cycle cost effective. It actually saves $41,053 over the course of 20 years. So that's, that's a positive win. Again, the initial investment cost, we're hoping that that's not something that Peters Township considers as the most important thing, because clearly our system is initially more expensive. Okay, next slide. I won't spend too much time on the next slide because we have other people that still need to come, but this really shows a simple payback. And to calculate the simple payback, we did it in both scenarios, and we were mainly looking at how much does System 1 save yearly in terms of energy and maintenance costs. And it's a simple calculation, so there's no net present value here. And in System 1, we'll just look at scenario 1. It saves $6,552 yearly over System 2. So to overcome that initial high capital cost, which is $98,000 more than System 2, it'll take 15 years for our system to become viable. In scenario 2, it becomes viable at year 18. And so what's really important here is that we want Peters Township to look at this system through a life cycle lens. We don't want them to just say, hey, this is too expensive up front, because in both scenarios, we are life cycle cost effective, and this system will save Peters Township money. It will reduce energy costs, and it will also, they'll have a system that doesn't need replacement as often as others. Next slide, please.
Thanks, Wojtek. Going with the economic solar analysis quickly, like I mentioned before, the ITC credit, 30%, could roughly save the township $300,000 if it's constructed by 2019 or starts construction by 2019. The reduced energy price under the PPA could save around $240,000 in energy savings throughout its lifetime. And also there's solar renewable energy credits that can be sold. Currently in Pennsylvania, it's $10 per SHREC. Going over the performance metrics over the 20-year lifetime, it has a current net present value of $625,000 with an internal rate of return about 22%. And also noted the investor will break even in year 2, and this is for the chart on the right is for the 500 kilowatt system. But also the investor will break even in year 2, even if the scale-up option is pursued with the 2,300 kilowatt system. And next slide, please.
Thanks, Kevin. We only look at economic feasibility of the horse. Greenhouse costs are relatively small, around $5,000, and we ignore them. Capital cost of the horse is around $100,000, and we assume that the feedstock will be free of charge, and fertilizer will be either used or sold to reduce expenses. Based on these parameters and assumptions, the horse would have a positive net present value around $27,000 with an internal rate of return around 14% at 20 years of operations. Payback time of the horse would be around 6 years. As mentioned before, the real gain comes from educational perspective of the systems. You cannot put a price tag for a well-educated population towards a more sustainable future. I will stop here and Elena will talk about environmental analysis of our project.
Great. Thank you, Gonka. So we looked at the environmental impact of the overall project. The Rolling Hills Park project is designed to be environmentally benign, self-sustaining, and offer minimal disturbance to the land and wildlife. So two key areas of interest were identified in the planning stages as a means to measure the project's impact on the environment, and those were air quality and biodiversity. These indicators serve as a measurement of success for the project for their lasting effects on the local ecosystem. So an LCA, or life cycle analysis, was performed to identify areas of opportunity where the park has control to mitigate risks, and also identify initiatives that are helping the project achieve its environmental stewardship goals. So highlighted in red are areas of opportunity, while the green represents positive outcomes of the project's air quality. Construction will involve a high level of greenhouse gases, even if green construction practices and energy-saving processes are employed. So the expected 283 metric tons of CO2 equivalent is higher than if we used wood or steel in lieu of concrete as our primary building material. However, alternative materials would not offer the same sort of like strong building envelope for energy efficiency purposes. Over the 20-year lifetime of the project that we, 20-year lifetime that we used for the project, 11,780 metric tons of CO2 equivalent from coal-powered electricity will be offset. The solar array will emit only 4% of the CO2 equivalent than, say, a coal-powered electricity option. Food waste for the biodigester will be diverted from landfills. Meeting just the minimum feedstock requirement will actually mitigate around 395 metric tons of CO2 equivalent over 20 years. And plans for lawn maintenance are currently unknown, yet the use of fossil fuel-based maintenance vehicles is assumed. So the life cycle analysis provided expected emissions for the use of these machines, and over a 20-year time span, this would produce roughly 25.2 tons of volatile organic compounds. And looking at biodiversity, biodiversity actually offers many benefits to the environmental health of an area and speaks to ethical, sustainable development. So similar to air pollution, construction will have the largest disturbance of the natural environment and has potential to harm the biodiversity in the area. With the goal to increase biodiversity in the area above current pre-construction levels, it is suggested that low impact development, or LID, be practiced. LID would harvest soil that would be typically lost during construction or eroded and store it for use in the native lawns. It is also suggested that loosening soil that was compacted by machinery or human presence be practiced as well. So native lawns planted will grow stronger using this native topsoil and will provide a natural habitat for native wildlife, insects, and migrating birds. Multiple studies show a positive correlation between native plants and biodiversity, where wildlife abundance, diversity, species richness, biomass, and breeding pairs will all improve. So on average, native wildlife populations were 4 times higher in native lawns than their comparative non-native counterparts. And besides expanding the area's biodiversity among native species, exotic wildlife populations have also been shown to decline in native meadows, reducing the overall number of intrusive species in the area. So with biodiversity having such a positive response to native plant species, it is suggested that an area's carrying capacity is actually determined by their plant choice. And with that, we're going to move on to our social and education considerations.
Thanks, Elena. Going over the social and educational benefits of the solar. Instead of just having a solar array sit in the field in the northeast side, we want to create an opportunity for the community to be able to learn the logistics of the system. So we suggest even having a case study on hand in the Nature Center about the array itself and how it supplies energy to the Nature Center, surrounding facilities, high school, etc. That ability to learn will be important. Also having information about residential distributed PV generation West Penn Power applications. Basically, a place where if someone was interested in installing solar energy on their home, they could go here and learn about solar energy and given the right tools and information of how to do that. So moving on to the next slide, please.
Thanks, Kevin. Okay, let's talk about possible educational programs that can be offered with biodigester and the greenhouse. Bottom line is, we want to show how can we reduce GHG emissions and also produce energy. Interactive tours will be a great attraction for people. Visitors could observe how leftovers from their table can fire up flames. Another activity could be for students of any class levels, encouraging students to take part in system operations would expose them to sustainable systems. Here are some examples of group activities. Bring Your RESS Day. This will spark interest among visitors. They will think twice before throwing away their waste. Another attraction will be Grow Your Experiment for students or kids in general. They could have planting and growing veggies and fruits in the greenhouse. Pick and grill could be a fun day. Visitors could pick veggies from the greenhouse and grill them on a fire-cooled biodigester. In short, performing demos of food waste management is a fun way of learning rather than reading textbooks. There could be even public consulting services to have people for developing their own biodigester and greenhouses. I will stop here and now let Kevin present our conclusions.
Thanks, Anka. To wrap it all up, basically all these technology designs maximize the efficiency of natural resources. They work in unison to help achieve a low to net zero carbon footprint. And spoken about before, overcoming the upfront capital costs will be important, and observing the life cycle cost is prudent. A lot of these systems will outperform and be more financially viable than a less sustainable option deeper into their lifetime. Aside from the technology designs, using the Nature Center to educate the community about renewable energy and sustainable options is also very important. We consider the Nature Center as a hub for learning, where even high school classes and extracurricular courses can be held there. Moving on to the final slide. Also, just the park in general. The Rolling Hills Park is a platform for sustainability. There can be numerous clubs, activities, promoting local growth, local businesses, and the establishment of community goals under the realm of energy efficiency, implementing sustainable technology, etc. And I will point out that Ed recently released a survey to township members. As you see on the charts on the right, it got a very positive response. A lot of people do believe that the Nature Center budget should incorporate sustainable technologies, and they value the importance of sustainable community development. And all in all, this is not just a proposal about implementing sustainable technologies in and around the Nature Center, but rather encourages community involvement and education for sustainable growth in the future. So we appreciate you all taking the time out to listen to our proposal, and we'll open the floor to any questions you might have.